Hi everybody, and I personally have a small problem with my presentation. The topic is so wide, it's so interesting for me, so I just created about 30 slides full of information, and it just won't be possible to squeeze everything into 30 minutes talk, but it would be a pity to throw away information. So I'm just going to skip slides as crazy, but original slides will be shared on a website inside you're just interested. So deep reinforcement learning, and it's the least important slide, but the image is kind of interesting because it's a personal reminder for me how hardware progressed over time for last decade. It's a real supercomputer system installed 12 years ago, and its total performance was 10 times less than just video card you can buy for $700. I find it amazing. So it's just real system used for numerical computation, and it was 10 times slower than just GPU nowadays. And this is also not very important slide. I just like this dog a lot and this meme a lot. It's really cool. And the rest are just my complaining about complexity of neural networks and the importance of intuition. You really need to understand what's going on with your models, what the theory behind these models, what you're expecting to get, to just make decisions about what to do when your networks is not working, and how to make them work better. And in my presentation, I will try to give more about information about intuition, how to understand what's the logic behind theory, maybe with some using not very precise math. And if you are a mathematician specializing in reinforcement learning, you may be not really happy about my presentation. So this is a slide which shows what's a problem we're trying to solve and why reinforcement learning is called reinforcement learning. And the basic model is the agent is communicating with environment, somehow using some actions and observing some state. And environment gives agent the reward. And our problem is to just how to maximize reward, how to act using our actions and how to gather as much reward as possible. And there are examples how to formulate some well-known situations and problems using reinforcement learning. I also skip it, and I also skip this. Maybe I should note just because reinforcement learning is important because it's something, from my understanding and my feeling, is something in between supervised learning when you need a lot of labeled data and unsupervised learning when you really not always know what you end up. And reinforcement learning is something between those approaches when you still have some driving reward value, but you don't need to label every example. And that makes it very appealing and very general and applicable to a wide range of topics and problems. And there is a notation used in scientific articles, and there are several quantities which are important, in fact. First is policy. Policy is our guideline, what we are going to do in any particular state. When we observe some state, policy gives us probability distribution of our actions, what we should do. Sometimes it can be deterministic policy, if it just says us, okay, do this. Or usually, most of the time, it's probability distribution. And next one is value. Value is just how much reward we're going to accumulate from this particular state in total. And Q is also very important stuff, and it's very similar to value, but it's also adds action from which we going to accumulate. And the central point in reinforcement learning is Bellman equation. Bellman equation has lots of forms and lots of interpretations, and there are very wide in literature a lot of various forms, but in fact the most, for me at least, understandable form of Bellman equation is here, and it just says that our value in our every state is just local reward plus best action we can do in terms of future reward given by all actions we should do. And this is my rough illustration how agent should behave. And Richard Bellman, who first proven and wrote this equation, he just proved that if we act according to this equation, we end up having an optimal policy, and we will end up with maximum reward, which is very nice because it gives us lots, just a way to solve those problems. And now I'm going to show you a bit of practice just to demonstrate how to what's possible and doable with these methods. There is nothing state-of-the-art here. It was in fact done by DeepMind guys 4 years ago, but it's a neural network with 3 million parameters. On the left, it's schema mostly contained by convolutional networks, and after about a day of training, it can learn how to play this. And you need to understand that there is no idea about ball, about its velocity, about paddle, is it good or not to break balls. It's just pixels observed by neural network and reward value given as every time you break the ball, break the brick, and just get +1 reward. That's it. And after a day of training, it can end up playing much, much better than me. And even now, observing this video, I just have feeling that it's in fact a person sitting and playing the game, and not a neural network with just 3 million parameters. Because it looks like it tried to push in the corner, just get more reward. And the most beautiful stuff about those algorithms that they very general. So you can take just these methods and apply it to totally different domain, maybe slightly reformulate your inputs, and it will solve your problem. At least it will try to solve it. Okay, this is not very important slide. It's about important to go deeper, and what quantities we can approximate with neural networks, almost any. And this is also not very. I've skipped a very important slide. So, how to solve these problems? How to train our network to behave optimally in terms of reward given by environment. In fact, there are two large different approaches. First consists on direct application of Bellman equation. And Bellman have proven that if we act according to this equation, we will act optimally. So to just act optimally, we need to know Q for every state, which can be a problem by itself, but those methods in first group are just approximating Q in some kind, and the better the approximation, the better our behavior. Second group is doesn't care about reward and Q, but more concerned about policy, because at the end, we still want to act. So we observe some state, and we need to choose some action. And the second group called policy gradients, and the idea is to just punish actions which let bad outcome and promote actions which gave us good reward. And those methods are policy gradient, actor-critic method, and the actor-critic method. This is a method which I'm going to explain in detail later. And there are some activity, very recent. Last November, DeepMind guys published a paper about their method which tries to combine those two approaches together, and they reported that it's that they got state-of-the-art result on most of Atari benchmarks, which is very cool. But as far as I know, there are no open source implementation of these methods yet. So it's something to be done here. Okay, this is not an important slide. This is also not very important slide because there are a lot of information about Q-learning and DQN algorithm, because it was historically first, and it's a lot of articles. You can easily find them, a lot of implementation of DQN algorithm. Policy gradient, this slide also not very important because I mostly said about it. So it's we just promote action which gave us good outcome. And let's go straight to actor-critic algorithm, which in fact actor-critic is not very correct name for it, because full name is Asynchronous Advantage Actor-Critic. And every word here has special meaning, and it's can be explained, but it's not very easy. So I usually call it actor-critic, and as far as I know, there are a lot of people just also call it actor-critic and don't care about the difference. So its ideas will be explained in details later. What is important is that this article doesn't give you any reference implementation. So mostly they just give you gradients which you're supposed to turn into your code. And it's not very easy, especially if you forgot your calculus. So to just clarify what's going on, let's try to get understanding what they trying to do here. So let's start from simple thing. What happening during playing when we are trying to exploit our policy? Let's imagine we have properly trained neural network and we want to play the game. How to do this? So at every step we observe some pixels from our emulator, and we feed those pixels into our network. Network in actor-critic algorithm has two heads. One head is used to approximate policy, which gives us probability distribution over our actions. And the second head supposed to approximate value of a state. It's just a single number showing how much reward we are going to accumulate from this state, at least from network's approximation, network's prediction of value. And during playing, we don't care much about value because value is used only in training as baseline. We more interested about actions. And actions is a probability distribution we need to sample to get concrete action to do. And there is very important to do sampling and not just argmax, because long time ago I just thought, okay, it's some probabilities, let's do argmax, it will be my action. It's totally wrong. You need to do a random choice, and that's important because nothing will work. So you sample, you get your concrete action, you feed it into environment, your Atari emulator, and your environment give you reward. Most of the time it will be 0 because reward for breakout, for example, is 1 only when your ball hits the brick. And this loop is repeated 25 times per second to just during gameplay. But if you go into train your network, you need to remember this experience in some memory buffer as chain of actions you did and what reward and what observation you experienced. And during training, first of all, you're calculating your discounted reward, which is just a sum with discount factor for every state. And we start training. So, as I've said, network has two heads. First is policy and value. And first expression in actor-critic gradients is just says us how to improve value prediction over time. So in fact, it's just regression problem, and just mean square error. It works really nice here. Second part is how to improve policy, and policy has exactly the same idea. We punish actions which led us to bad outcomes, and improve probability of actions which turned out to be good over time. And we use our discounted reward minus value predicted by network, and this entity, this called advantage. That's why it's called advantage asynchronous actor-critic algorithm. And there is third component of loss function of gradient optimization called entropy, and it's in fact just some form of regularization, and it's kind of important, but it's used more to prevent your network from being too deterministic, so to push it into exploration of the states. And the idea is we just trying to maximize the entropy a bit, and when network is not really sure what action to do, we just switch it into exploration mode. And according to implementation, it's possible to do it two ways. First of all, you can calculate the gradients by yourself, and this method is proposed by DeepMind guys in their paper, and this method is much more scalable because you don't need to pass all pixels into central place and do training on GPU. In fact, they did all training only on CPUs, and it worked much better than previous method and converged faster. But from a mathematical point of view, it won't be any difference if you just reformulate those components and optimization gradients via loss function and do training in one central place. It will be exactly the same gradients. And this method this way will be much, much simpler because you don't need to mess with manual gradients. You don't need to implement your own optimizer because not all toolkits, especially keras, for example, supports manual tweaking with gradients as far as I know. And that's it. And you need to be aware that A3C method has asynchronous in its name. So one of the idea which stabilizes the network a lot was with exploring and gathering experience not from one single environment, but from many environments at the same time, which gives much better and diverse experience and stabilizes and speeds up reconversion. So implementation, proper implementation, should be aware of and support multiple agents playing at the same time and doing optimization. So, yeah, and that's a training network. It's a graph. It has exactly the same amount of parameters as plain network, just extra expressions for loss components and extra inputs gathered from experience. So that's it. And there's this list of things I'm measuring in my code and showing it in TensorBoard graphs, because it's in fact very important to measure and watch for various components of your loss function, for your gradients, because they shouldn't be too large or too small. And you need to understand what's the expected values and how they should behave and how to tweak them. And there is a slide not related to reinforcement learning, but if you ever try to make TensorBoard work properly with keras, you may notice that its support is really, really bad. And there is a solution how to do proper monitoring of any tensor in keras and pass it into TensorBoard. It's a bit hacky, but it works. I'm not going to explain it in details, just refer to the slide. It's enough information. And there is a link to my implementation, which has Actor-Critic without parallel processes. I don't know, I call it A2C, but it still works. It still converge much slower, but it can solve Atari games. And it has deep Q network implementation, and I try to keep it as clean as possible and as small and understandable. So I think, in fact, its core code is about 300 lines or something. And there is second part of my presentation, and which I'd like to describe how to apply reinforcement learning ideas in more or less practical real-world problem. I'm working in a company called Farnova, and our specialization is extraction of data from websites and analysis of it at scale. And our primary interest in hotel websites. So the problem is, imagine you have hotel website and you want to extract room prices from it for a specific set of days, like next weekend. You need to fill check-in date, check-out date, click a couple of links, maybe select some hotel, which specific hotel you're interested in, and then you get list of prices with rooms with prices, and you want to just extract it. That's maybe quite simple for human, but imagine you have hundreds of thousands of hotels with different websites, with different web design, and you want to do this data extraction on regular basis, which is in fact quite hard. And you want to automate it as much as possible. And so we try to apply reinforcement learning to web page navigation. And in reinforcement learning formulation, it looks like this. So agent is browser, environment is website logic, state is web page, actions are clicks, form fields, all stuff user can do in the browser, and reward is the information we are looking for. So it's a final destination, either +1, either -1. Agent need to or wants to find. And I'm going to skip this slide. In fact, it's very interesting. I'm encourage you to read more about OpenAI Mini World of Beans benchmark. but I don't have time for it. And to just start working in this direction, how to use web page navigation, how to solve web page navigation problem using reinforcement learning, I implemented my own small benchmark with small set of browser-based tasks an agent supposed to learn how to solve. And it varies from very simple, just click a proper link, to quite complex, like selecting proper date in a calendar, toggling checkbox, and clicking submit. And it need to click a specific date on a calendar to get positive reward. And it was a network. In fact, it's just actor-critic network, very small, 90K params. And it was a bit of tweaking about how to feed web page elements into the network, because web page can have variable amount of elements, but it's solvable. A bit hacky way, but it was done. And I'm not sure it's visible to everybody. In fact, the most important charts are 3 charts on the right. They show amount of reward, maximum amount of reward, mean amount of reward, and minimum amount of reward gathered by agent in a training episode. And you may notice that even maximum amount of reward in the beginning of training was really, really infrequent. These charts are training process for the hardest problem in my benchmark, which involves calendar, which you need to select proper date, toggle a checkbox, and click submit. But over time, it starts to figure out how to do it more frequently, and it starts to grow, and finally it discovered how to do it all the time, at least once, because it's maximum. And at the end, I think it took about an hour to train properly. It discovered optimal policy, how to click and always get to the reward. And other charts are showing just various components of actor-critic, like entropy loss, policy, and value loss. So of course it's just an intermediate result. It may be even just first step into solving it properly, because it's just a tiny benchmark. But it shows, it gives some encourage how to solve this complicated problem in reinforcement learning way. And we definitely going to move in this direction. So thank you very much. If you have questions,